sir. So, I am making you as a co-host, sir. 1 second, sir. Co-host or make host, sir? Shall I make you host, sir?
Hi there.
Hello, Jan Michael.
I can't hear you, I
it's
guess.
okay.
So wait.
Yeah, thank you.
Hello.
Yeah.
Jan Michael, welcome to this meeting.
Okay. Hey.
Welcome to this meeting. We are online. This is Pranav Deshmukh here.
Somehow I can't hear you guys. Oops. No. Okay.
Okay.
Yeah. Very good.
Okay. All right. Okay, good. We are connected.
Yeah, that's
Yes.
Yeah, this is Sunil from ISER Tirupati.
Sunil is at another institute in Tirupati. There are two institutions in Tirupati. One is the Indian Institute of Technology, and the other is the Indian Institute of Science, Education and Research. So both are amongst the premier institutions in the country, and we are very fortunate that both of these institutions are side by side here in Tirupati. In fact, Tirupati is the only city which has ISER as well as Tirupati. So Sunil is on the faculty at ISER, and I think you know Vinay, but Vinay was to join the meeting, and there is a last minute personal emergency. His son was not well, so he called me a little while ago, and he has I think his son has to need some immediate attention. So Sunil is taking care of that. So he will probably join as and when possible. There is some chance that he might be able to join even by 2:30 by the time the meeting starts. I also see Arvinda in the audience. Arvinda, can you unmute yourself? So Sunil is an AMO scientist. He works in various theoretical and experimental aspects. He's building some nice experiments. So Sunil can tell you about it.
So this what we are building here is an ion trap setup, a multiple radio frequency ion trap to confine ions. Right now we are focusing on biomolecular ions, gas phase biomolecular ions, such as amino acids and peptides, nucleotides. So we confine them in a 16-pore ion trap, and then we study the interaction of light with these molecular ions, their photo detachment, photo fragmentation, and fluorescence emission. So these are a few things which we are interested in. Yeah.
Very good. So, but you don't use intense lasers, you just use single photo ionization or absorption.
Yeah, this is with the laser, but it's right now we are focusing on the negative molecular ions, deprotonated ones. So just removing a proton, we make it a negative ion. So the technique we use to generate these ions is called electrospray ionization. Maybe you have heard about it. Yeah, so they can generate these biomolecular ions in gas phase as a negative ion, and then we can store them inside the ion trap and to photo detach them. So we need usually UV energy photons, so which we can get from some lasers, and so we use that, and we are actually planning to measure absolute photo detachment cross section using this ion trap technique. The absolute measurement of photo detachment cross section is not
It's hard.
available for any of the complex molecules. So this is what we are planning to do in our laboratory.
Ah, good. Yeah. Very good.
Yeah.
Yeah. So before
So
we start,
maybe we can test the presentation of
yes,
Professor.
yes.
Ah, okay. Yeah. Let me see how this works. It says host disabled participation screen sharing.
Okay. I think I need to make you as a co-host. Yeah.
Yes.
Yeah. So I think right now you will be able to present, I guess.
Okay, let's see. Yeah, this looks better.
Yes.
All right. And now we make this. Like this?
Yes. Yeah.
Okay,
I think
well,
this is the first slide.
No, it's not the first slide.
No, this is.
Oh, no, it doesn't work. Ooh. Stop sharing. Okay, maybe yes. Yeah, so now. Screen. Now it's better, huh? Can you see it?
Yeah. Yes, we can.
Okay.
Right.
Cool.
Yeah. This.
So I stop
this-
again, right?
Yeah. This looks like your first slide.
Yeah.
Yeah. But you can go full screen as well. Yeah.
I think I did full screen, no?
Yeah. Earlier it was, and then when the first slide came, it was not the full screen.
Really?
Yeah, you can perhaps present the entire screen.
Yeah.
So now it's not full screen?
Yeah. Now it is.
Yeah, now it is full screen.
Yeah.
Yes.
Now
Yeah.
it is.
Now it's fine.
Okay.
Yes.
Perfect.
Yeah.
Yes.
So, Professor, is it okay to make it a YouTube live?
I personally don't like this, but if you really want this, yeah, I can do it.
Okay. So we usually make this on talks available online in YouTube. So only with your permission. So you will be doing it.
Yeah, but this, so can you limit this like to 2 months or something like that? Is that possible? And take it off after 2 months?
Okay. I think, I mean, if it is, Deshmukh, what do you suggest?
We can do that. I mean, we can certainly do that. Why not?
Yeah.
Yeah. So I think everybody who really missed it or really wants then can see it.
Yeah,
but I'm not very, how to say, I don't like these kind of corpse of talks hanging around in the net like 10 years after or so on.
We can certainly do that. Sunil will
Thanks
just
so
make
much.
a note of this, and we'll take it off after 2 months. So
Thanks. I appreciate it.
Okay, sure.
Yeah.
So right now it is not on YouTube. If it is okay, then I can keep it on YouTube live.
Yeah. For 2 months you can keep it alive.
Okay, great. Yeah. So that we can do. Yeah, that we.
Yeah. So there are some graduate students in the audience, Jan Mikkel, and there is also Professor Arvind from IIT Madras.
Yeah. Hey.
There is Dr. Arvinda from IIT Tirupati. He works in the field of quantum information science. Arvinda, yes, there he is.
Hello there. Hi
there.
Yeah, so Arvinda works on quantum information science, and there are a few others, including some graduate students. So Sunil, are we ready to start? It is nearing 4:30 in another minute, I think.
Okay, yes, sir. So I was, for a live YouTube live, I need to log into the IIT Tirupati account. Right now it is not live. I just
you have the credentials, right?
Yeah, So maybe I will just use the one that Vinay sent me.
Yeah. So Vinay was going to handle this part, but he had to take care of his son.
Okay. I
at a
think
short
Vinay
notice.
already sent me. Let me check.
Yeah. Do you have it?
Yeah, sir. I am going to log in. In 1 minute, it will be ready. Yeah, I think I have the information.
Good.
Okay, I think that is not for the YouTube, but this is just for the Zoom account. These accounts are different. Maybe, I mean, this is right now just a recording version.
Yeah, so I think if it is being recorded, we are good, Sunil. We'll just go ahead with the talk.
Yeah, right
and
now
we can
maybe we
upload
can
it
just,
later on the YouTube.
Yeah, that's okay. Yeah. Okay, maybe we'll do it later,
And
Jayaprakash.
then,
Yeah, thank you.
we can keep it on the YouTube for 2 months,
Yeah.
and we can upload it after the talk, once
Yeah,
the technical
sure.
support is available.
Okay, sir. Yeah. Okay. I think now we can basically start.
Yes, so very hearty welcome to everybody to this talk by Professor Jan Michael Rost that we have been waiting for. He is the director of the Max Planck Institute for the Physics of Complex Systems for quite some time, and also a professor of theoretical quantum dynamics at the Technical University in Dresden. He studied earlier at Freiburg and continued research at the University of Washington, at Seattle, at Harvard University. And he has, apart from his very distinguished research that most of you will be familiar with, he's also contributing a lot to the physics community, and like editorial boards of journals. He is the lead editor for Physical Review, and he's also the dean for the Max Planck Schools, which offers training to international students in Germany. His research interests, I'm sure, are very well known to everybody over here in the audience. He is one of the world's leading authority on ultra-cold and ultra-fast dynamics of finite quantum systems, their interactions with the environment, ultra-cold Rydberg dynamics, and interaction of clusters with ultra-short laser pulses from terahertz to X-rays from, like the free electron laser source. And he's also addressing some very fundamental questions in physics as to the emergence of time and so on. So I would not come in your way between you and Professor Rost. Welcome to you once again, and you may please take over.
Yeah, thank you very much for the invitation and also for the nice introduction. So I'm really kind of pleased to see that you guys work on Saturdays and come to a seminar. This is something you would not be able to do in Germany. So it's great that you do this. And I'm very happy to have the opportunity to tell you a little bit about what we have been thinking recently in terms of the dynamics of delocalized electrons. Hopefully you can see my screen.
Yes.
Okay, good. And of course, we deal mostly these days, as it was said in the introduction, with like short laser pulses, and that means also strong laser fields, because otherwise you don't get really photons into your target in a very short time span. And that means often time-resolved dynamics. But since this implies nonlinear interaction of photons with your target, that means many photons, the dynamics is quite intricate sometimes, and that makes it, of course, interesting. And as I said, recently we have been starting to think about delocalized electrons in strong laser fields. Atoms have mostly localized electrons, condensed matter systems have delocalized electrons, and this makes a difference. And this kind of difference, what this means for strong laser field excited delocalized electron dynamics we are interested in. The projects I will talk about today have been carried on under the supervision of Ulf Salman all the time, by Hamed and by John Yu. These were two postdocs who are by now back in China with John, and Hamed went on to another postdoc in Germany. And experiments I will briefly mention have been carried out in Lou DiMauro's group in Ohio State University in the US. Okay, so this is the menu. So I give you an introduction about intense light matter coupling briefly, since I kind of think you're not so familiar maybe with the fundamentals, so that will be very brief. And then I have two topics: high harmonics of delocalized electrons, and that leads to backscattering systems with broken periodicity, and valley polarization in graphene with ultra-short linearly polarized pulses. This is a kind of topical thing. Graphene and systems without band gaps, 2D systems, two-dimensional systems are very popular. And as you will see, it came to a surprise that you can address valley polarization. I will also explain what this is, with ultra-short linearly polarized pulses. Since valley polarization is linked to kind of chiral almost properties, people thought one can only address valley polarization with like circular polarized pulses. Okay, so let's get started. What is intense light matter coupling? So to that end, we can look at the characteristic scales first of a free electron in intense laser field. So let's take a very simple Hamiltonian here for one electron. You're used to this: kinetic energy, some potential where the electron is bound to, and then it's coupled, typically in dipole approximation, to an external electromagnetic field. It's just the electric field amplitude here given in the right. Linearly polarized, let's say, by some envelope shape G of t, and of course cosine omega t or sine omega t. And now, how does basically the light couple to the electron? This is given by this term, and what this affects is essentially that the potential is shaken up and down here. You see, this is typically, let's say, a Coulomb potential for Coulomb interaction of the electron with an ion. And this R times F field kind of bends the potential down if cosine is large. And then if it goes to the other half period, it bends it to the different direction. And the nice thing is that one can treat this kind of dynamics to a very good extent semi-classically with classical trajectories, because you put a lot of energy into the system, as you will see. And oops, the typical scales here are the following. So let's say, ask ourselves, what's the length scale of the electron exposed to a laser field? So that to that extent, I mean, to this end, we just get rid of for a moment of the potential and just think of a free electron moving in this kind of laser field with the Hamiltonian kinetic energy and this laser field. And then you see this you can solve immediately, classically and quantum mechanically, simply by integrating the equations of motion. P dot equals just f of t. So you integrate this and then you get the momentum. So the typical momentum is something like f over omega, because if you integrate cosine omega t, you get 1 over. So that's the momentum scale, momentum electron scale in units of the laser properties, basically peak field strength here and frequency. And if you integrate this again, momentum is also velocity, then you get the spatial scale, the distance, and this gives you another omega in the denominator, and this is called the quiver amplitude. This means you go back and forth with your electron in the laser field. It's shaken basically by the laser field, and the distance it travels by this shaking is given by x quiver. And finally, the energy scale is a²². That's simply the average kinetic energy the electron has in this laser field. Now, what does this mean quantitatively? Let's take a typical laser intensity. That's basically F0² here of some like 4.6 times 10 to the 14th watts per square centimeter. This is easily achieved these days in basically femtosecond lasers in labs. And at a frequency of 800 nanometers, that's 1.55 electron volts. That also is typical, and this is not so much set or driven by physics. This is really driven by the possibility to generate this radiation with Ti-sapphire lasers. Now, if we take this, then this translates to a quiver motion of 35 atomic units. So you see this is quite substantial if you compare this with the size of tightly bound electrons in atoms. A momentum of 4 atomic units, which is also quite a bit. And the ponderomotive energy is just 1 atomic unit. This is why I chose 4.6 times 10 to the 14. Could have chosen something else. And that means, and that's very important, that indeed your interaction is non-perturbatively with your bound electron. And that makes it interesting and also set quite intricate sometimes. Just to give you, again, a feeling for the scale, if you think what you would have in terms of electric fields without your laser, then if you think of a classical electron orbiting your proton for hydrogen at the typical distances in the ground state, then 1 atomic unit, this is the atomic unit of field strength, corresponds to an intensity of F0² of 10 to the 16th watts per square centimeter. So this 4.6 times 10 to the 14 is already non-perturbative. That means you exchanged quite a number of photons, not just a single photon as we have been used to for a long time. So which kind of dynamics does this lead to? Let's look at this here. As I said, so first of all, of course, this will kind of liberate or free the electron, but in an unusual way, not just by absorbing photons and getting a higher energy in the continuum, just adding up the photon energy to the basically bound energy of the electron. No, you get something which is called tunneling ionization. That is, if it is the time or the phase here where the potential is bent down by the laser field, then the bound electron can tunnel here through this barrier and gets ionized in this way. This is called tunneling ionization. It happens under certain circumstances, of course, of the laser field compared to the binding energy. And what is important is that this happens on the scale of this quiver motion of the electron quivering in the laser field, basically at 0. Of course, it happens at a finite distance here, but this is very small compared to the quiver amplitude to the 35 units or something like that, or even more. Okay, then let's see what process do we have. Typical process, which you all know, is high harmonic generation. That's typical nonlinear light matter coupling process. And what this means, you first tunnel out, and then your ionized electron is driven back to the nucleus by the force of the laser field, by this R times F field. And if it kind of is in the vicinity of the nucleus, it can recombine and emit then, due to its velocity or speed it has, high frequency radiation, multiples of your base frequency here of the laser, and this, therefore it's called high harmonic generation. And the typical spectrum of the high harmonic generation looks like this. So this is, of course, here logarithmic scale. So you see it's not that efficient, but it doesn't matter. One can do these days still very efficient high harmonic generation. And essentially all our attosecond pulses, which are even shorter by 3 orders of magnitude than the femtosecond pulses, are really based on this harmonic yield and a few high harmonics here. So you see initially you have a drop, then you have a typical plateau. And then we call this a cutoff. Then after this plateau, the intensity suddenly kind of falls down to basically negligible emission. And this cutoff is a classical condition from a trajectory, but it would never appear if you really treat radiation purely classically, because it would simply exponentially decay. Here, this plateau is the consequence of an interference. It's the interference of your continuum wave in the laser field of the electron and your bound orbital. And the interference term of these two gives you basically then this plateau here. So you can have another process instead of the electron turning back to the nucleus, which is not so likely as you just saw. I mean, it was a logarithmic scale for the radiation. Of course, it simply can get ionized, which is called above threshold ionization, or simply photoionization by a strong laser pulse, which just goes out. But even this is structured, the spectrum. You can see this here. So this is the photoionization spectrum for xenon. Yeah, again, similar intensity, linear polarized and circular polarized. And you see there's a big difference here. And the difference is, again, circular is very boring in a way. It's just exponentially going down, which means the electron just goes out. Now, this reminds you of high harmonic generation again. And the reason is actually really a similar one. Also here, the electron comes back, driven by the laser pulse, but now it does not get rebound or captured. It actually elastically scatters from the ion core, acquires even more energy by turning the momentum around in the laser field, and then gets this higher cutoff here. Also, it goes down eventually because here it cannot rescatter anymore. And this cutoff is roughly 10 times this ponderomotive energy, the typical energy scale of the electron in the laser field, which is here 45 eV. So these are the two basic processes, high harmonic generation and high above threshold ionization. It's called here HATI. Now, this was my introduction. So what are we interested now to do with this? So we ask ourselves, for a laser of a field strength of F and the frequency omega, we have these two characteristic scales I told you about: the spatial scale, the quiver amplitude, the momentum scale A, momentum vector potential. And the question is now, how do these fundamental scales relate to structural properties of matter in the context of delocalized electrons? So in which observables do these scales become actually apparent? And if you think about it, for atoms, the nonlinear coupling to light, that means HHG and ATI, requires the return of the laser-driven electron to the nucleus. This is called rescattering. We just talked about this. But the quiver amplitude itself is not relevant due to the small extension of the atomic electron cloud. Yeah, this is also that this tunneling essentially occurs at zero. And what actually matters here is that the vector potential A, that determines the momentum transfer. This is kind of the momentum you can exchange with the light field and transfer it to the electron. So what's then the role of the quiver amplitude? I mean, clearly on the scale, the atom does not have a scale, a spatial scale, it's simply zero, but you can think for other atomic systems, for instance, a cluster, that is certainly extended and could basically reach extensions which are kind of comparable with the quiver amplitude. And here you see an experiment published in 2020 with our colleagues from Ohio. They did the experiment. And this is really now backscattering of localized electrons in extended systems. So these are argon clusters. You see for comparison here the photoionization yield for the monomer in black. And then you see clusters of different sizes here. And here you see, this is an experiment, and here you see theoretical calculations. That's essentially classical trajectory calculations for certain quantum elements for the initial absorption. And you see here cluster sizes, which roughly correspond here to these nanometers. And you see qualitatively a similar behavior. The difference is, of course, that here the dynamical range is for an experiment already extremely high. 6 orders or 5 orders of magnitude could actually be captured experimentally. But in order to see the interesting stuff where it actually stops your spectrum, you need even a larger dynamic range. At least this is what theory predicts, as you see here. So this is the range of 8 orders of magnitude, and here we have 6 orders of magnitude. But why do we actually get here again this kind of plateau, and why do you actually get higher energies if the cluster is larger? You see the green one has the highest energies, and the red one, the smallest ones, it gets systematically larger, also compared to the monomer in the experiment, of course. Now, the answer is very simple. And this is, I told you in the atom, what happens with this above threshold ionization, the electron gets tunnel ionized, it comes back and elastically scatters here from its ion and acquires even more energy. But now, of course, there's more freedom. You can rescatter from another atom in your cluster. And this leaves this delta L in comparison to an atom. And this gives you basically higher cutoff possibilities. And so the cutoff can be extended then by simply in perturbation theory, if you will, by this kind of extension. And the typical value here, how this grows the cutoff, is some scaling value here, but then in terms of the scaled radius of your cluster. So R over quiver motion. And this you can derive analytically under some assumptions. And there you see all of a sudden now the quiver amplitude plays a role. And to demonstrate to you that this is really true, the only thing what we do here, since we have this insight, we basically scale our energy by the ponderomotive energy, the 10 UP. And then you see it really becomes universal. So this is the effect of this growth here. And this is true in experiment as well as in theory. And this also tells you that not only at the cutoff, but also already below in this kind of plateau region, the dynamics is really driven by this backscattering dynamics and becomes universal once you scale it in an appropriate way in the experiment as well as in the simulations. Okay, so this was just warming up. This was basically what happens, which kind of role the quiver amplitude can play for extended atomic systems where the electrons are localized at the atoms. And now we really come to delocalized electrons. And for that, we ask ourselves, of course, if you have a typical condensed matter system, which is periodic, then this does not necessarily have a length scale. Or again, in a similar fashion as for atoms, the length scale you have is the lattice spacing, and the lattice spacing is typically much, much smaller than the quiver amplitude. So therefore, the quiver amplitude should be irrelevant for that due to this mismatch in the length scale. And indeed, the laser-driven electron dynamics takes place in reciprocal space. And the typical way how one can describe this is you take a time-dependent crystal momentum. Normally, we have the crystal momentum in time in reciprocal space, and just add this vector potential of the laser pulse in the bands. We will come to this. So the question is, when could the quiver amplitude play a role? And again, what we do, we introduce an external spatial scale. In that case, in the simplest possible way, by examining a finite chain of atoms with a length L. So we don't take an infinitely extended periodic system, we take a finite chain of atoms. And one more theoretical slide, how could you think now about these strong field processes in momentum space? Because I told you, of course, about tunneling ionization and recollision, recombination, all in real space, shown here again for atomic high harmonic generation. You can translate this already for atoms or atomic electrons to momentum space. And that looks quite interestingly in a similar way. And now, again, still you have energy, of course, in the y direction here also. And now we don't have here x, we have here momentum k. And then you can think of one band. It's a strange band. It's the parent ion. It's basically the binding energy of your electron. And this doesn't depend on the momentum. But of course, in the continuum for the ionized electron, you simply have a parabola. You have a very simple dispersion relation, just p squared half. And that's the parabola, the energy here. And that's basically your second band. And you can describe atomic high harmonic generation just with two bands. And you have the tunneling from the flat band of the bound electron to basically the ionized continuum electron here. And recombination is then simply by creating this hole here, and the hole recombines eventually, and this gives you the high harmonic radiation. Now, for a true kind of condensed matter system, you don't have these simple bands. You do have a valence band, which has some curvature, some dispersion, and you typically have then the conduction band. And you can, of course, put your electron here, create the hole here. And so this is called interband polarization. And again, it happens by tunneling, and you can have the recombination in a very similar fashion as described here in momentum space with the atom. Only the bands have a more complicated dispersion. And that, of course, introduces a certain effective mass. You're probably familiar with this concept. And that means your quiver amplitude is no longer as simply related to your vector potential A as before, A over omega. So you have an effective mass here. But that's about, in a simple way stated, the only difference. We'll come to others in a moment. So we describe our nonlinear coupling to light in a band picture in momentum space by using this Bloch's acceleration theorem. I mentioned this already, simply replacing K here. Now coupling to the laser field by K plus A of T. And like always, the field strength is dA by dt. And the position space trajectory, you can also, of course, calculate a position space trajectory, but now only directly from the bands. It's simply given by taking the dispersion of the band energy, the derivative of the band energy with respect to K is the velocity. And if you integrate velocity, you get distance, and that makes basically an effective trajectory here in terms of which distance it travels. Okay, and now we ask ourselves, what's really the role of the Quiller amplitude? And we will do this with a chain of atoms, which breaks this spatial spatial asymmetry. So I show you right away results, but we dwell a bit on this so you don't get lost, hopefully. So here we have now our chain of atoms. These orange points are atoms. They have a regular lattice spacing, if you wish, of 7 atomic units. That's kind of a typical thing. But the chain ends at some points, of course, or it's infinitely extended. Of course, we kind of take this infinite extension, the condensed matter limit, if you wish, as a reference point. So the harmonic yield is calculated by essentially integrating the electron flux and taking the Fourier transform. This gives them the frequency spectrum. That's a time-dependent electron flux. And that's just a window function for technical reasons and visualizing things. And of course, it's normalized. And here you see the result. That maybe looks a bit boring, but maybe not, depends on your perspective. And the gray kind of filled area here, that's the periodic case. And yeah, so you see a certain spectrum, looks a bit different than for atoms, but also it kind of goes down here, has no amplitude almost or no intensity up here. And if we take a long chain, long means that basically the total length of the chains, n times d, roughly, number of atoms times the lattice spacing is much larger than the quiver amplitude or twice the quiver amplitude, then this corresponds very much to the periodic case. This is what we probably would expect. And you see the structure here of the spectrum has kind of 2 characteristic drops. We know this already. These are cutoffs, which also occur in the condensed matter system. And we can understand this now in the band picture. So we have here our valence band, as I said. This is where the electron sits. You create an electron hole pair by tunneling, put up your electron here to the conduction band. And now it travels with A of t of the laser pulse. And if A of t is not large enough here, here's no resistance. So here you get kind of the plateau. But in order to get higher energies, kinetic energies, upon recombination, you would have to tunnel here again. And that means it drops again here. So you have a first kind of drop by the tunneling, and then you have a second drop here by getting to the next higher conduction band. So this is the situation, and this was here for 3 1200 nanometer radiation. So that's a bit longer wavelengths than the typical 800 nanometers. And you see the vector potential has been fixed now to 0.2 atomic units, while the wavelength is variable. We take a 4-cycle pulse roughly, and the model has 4 electrons per atom, but that's not so important. It's really one active electron only in the end, which plays a role. But these are very standard kind of parameters which are easily achievable in the lab. And why do we keep now the A0 fixed? Because really the vector potential is now the essential thing which really couples to the condensed matter system. Now the interesting part, yeah.
Hello, Prof. Rost. There is a question.
Yeah.
From Arvind.
Okay, am I audible?
Yeah.
Just a small question here. This periodic, when we say periodic, it is in infinite. When you how do the periodic and n equal to 160 differ?
So periodic is really with periodic boundary conditions. Okay. So this is what one normally would do. It's infinitely extended if you wish.
Okay.
And the n equals 160 is simply explicitly calculated with n equals 160 atoms.
But they are also periodic, but they are finite in length. That is what
I mean. Within the chain, it's periodic, but it's not overall periodic. So periodicity is really broken. I mean, yeah. But the point is that essentially the chain is so long, so that basically the electron quivering here will not explore the ends of the chain. So
exactly,
essentially more or less like an infinitely extended system. Okay. This is what's proven here, by this comparison.
Yes. Yeah. Thank you.
Something like the cyclic. Somewhat like cyclic boundary conditions, maybe.
Yeah, periodic boundary conditions, exactly. Yeah. This is how this is done theoretically.
Yeah.
For the gray case. Yeah. So you can ask me. It might take longer than, but you're very welcome to ask me. Of course, please do so.
Yeah. Thank you.
Okay, and so this is now the overview. If we kind of change our system size. So I told you we took here the blue spectrum is 160. This is the upper line here. Yeah. This would be the spectrum. And that's now a 3D representation where we have the spectrum harmonic order. In addition, we have here on the y-axis different system size. And you see, if we make the chain smaller and smaller, nothing much happens here until we come into this region where somehow the length is comparable with the quiver amplitude. Then all of a sudden we get drastic changes here. Yeah. And this is what we explore now. So if we take basically here, this kind of system size, I think it was 32, it's set here, then you get this kind of harmonic spectrum. So you get an extension of your plateau and it drops down here. Question is, where does this come from? And this is now quite interesting, at least we think it's interesting. This really comes from backscattering of the end of the chain. So this is what I told you in atoms, you can bump with your ionized electron into the ion and get elastically reflected. But for ions, for atoms, this only leads to a larger kinetic energy in the photoionization spectrum, because there's nothing to recombine if the electron flies away from the ion. Now here you acquire also from scattering at the end of the chain a higher momentum for the electron, but since it's an extended and coherent electron system, this kind of atomic chain with the energy bands of the electrons, you can recombine with your backscattered electron, backscattered into the chain. And that leads to this extended cutoff here. And if you look at the dynamics in the band picture, that's very easy to understand. So again, we tunnel in the beginning from the valence to the conduction band. We get here transported by A of t. And now this you cannot see, but because in space somewhere here, let's say, is the end of the chain. And then you can get elastically reflected. That means your momentum ends up here, but then gets further on transported and even beyond basically the next band gap, because there's still enough A of t available, and you end up somewhere here. So what's the limit? What is really then this cutoff here, this omega 1 prime? It's actually given by the vacuum level of energy for your electron in the finite chain, because you can, of course, only rescatter at energies where the overall electronic potential is still negative, right? So the electron is still bound. If you rescatter at energies which are higher, then you simply go beyond the end of the chain with your wave packet and it will not be rescattered. And therefore, the limit is set here basically by the vacuum level by this K value. And that sets then in the end this new cutoff. So this we found is an interesting finding. And what you can see here, this is really universal. So now we define simply, let's say, an effective number of atoms in the chain related to the quiver amplitude. Yeah, you divide the quiver amplitude by the lattice spacing. These are the typical scales of your system: quiver amplitude from the laser, lattice spacing from your target. And now if you fix your chain length to a certain ratio, or a scaled basically chain length with this effective length set by the length scales, and plot basically different now harmonic spectra against the harmonic energy. That's important, no longer harmonic order, but harmonic energy. And then you see this gives basically equivalent spectra. So the dynamics is really, really the same. What you have to do, of course, to fulfill this, if you changed your number of atoms in the chain, you have to change your wavelength, in order to keep this ratio fixed. And this is what you see here. And since the tunneling is more likely if you have a higher intensity, that also means that essentially then a shorter wavelength gives you the higher yield. But the shape, the dynamics is very, very similar. And this is always here kind of structured by the cutoff through this backscattering at the same position in energy, of course. And here you see again that when you are resonant, quote unquote, that means when this is roughly equal, the quiver amplitude, this kind of effective, number of atoms to the true chain length. So this is, if this ratio is roughly unity, then you get the best kind of yield of your harmonics. So that's very nice. And we kind of understand this here. And what is now for understanding, even in the periodic case, very important, is the relation to this trajectory picture. So it was very nicely developed, and I described this in the beginning a little bit to understand high harmonics in condensed matter systems with a trajectory picture. And this is shown here again. Now here you have the harmonic energies as a function of time resolved in the laser cycles. They're emitted. You can simply do this by this integral I showed you in the beginning and having this window function in time. So the background, the 3D density, is the quantum result. And here the white lines are trajectories and the black lines as well. Trajectories in this picture of the bands I told you about. So this is the spatial trajectory here. And what does this mean here for our chain? Essentially, our electron and hole trajectories, they go into different directions due to the dispersion. And the interesting thing is, now, of course, you have a spatial restriction because here is the end of the chain here as well. And that means here trajectories get reflected. This is our picture, elastic momentum exchange. So elastic reflection of the momentum, and trajectories go back, and here they recombine. And if you do this with like initial electron hole separation of 0, this is what one would do in an atom, I told you, because the scales differ so much and it's not important really, this tiny little separation at the tunnel exit, then you get the white dots. This is what was known basically before we did the study. And you see this doesn't match very well, it doesn't match at all, you might say, these fingers here. But if you have a finite initial hole separation after tunneling, then you get the black traces, and they really trace out the quantum result much, much better. And what is this finite distance implying? This is not just fitted or so on, this is really calculated. It's really the tunnel exit, or basically the distance, the vertical distance the electron hole pair has traveled while basically going through the tunneling process. So it basically appears at the tunnel exit after a certain time. And this time means it has already traveled a certain distance. And this is this initial separation of electron and hole when they appear here after tunneling in the conduction and valence band. And this fits then very well, as I said, with the quantum results. And it has also a nice meaning. You can guess this almost. It's very similar as in atoms. So this distance after tunneling, the tunnel exit, if you wish, even in condensed matter systems, is given by the band gap energy. Here, this difference in energy divided by the peak field strength. So that's the distance which comes out. And interestingly, the same trajectory condition also applies for backscattering in a periodic system, or not backscattering, just for tunneling ionization in a periodic system. You see this here. And here the effect is not so drastic, but this is the original kind of trajectory picture where the trajectories of electron and holes start at 0 separation. And this is with the new true tunnel exit. Here are the trajectories. And this is the black ones. So they really match much better. And therefore you can say that you have a very subtle spatial dependence in the strong field process of high harmonic generation in condensed matter systems, even in periodic ones, in the sense that you need this finite tunnel exit to really describe this well in the trajectories. Okay, so just one quick mentioning, if we relate this basically to impurities, so you might ask this yourselves, what do impurities do and how is this different from backscattering? And this you see here. So what we do here now, I should go back maybe briefly. So this is our chain, and the only modification we introduce now, we basically have one gap here, or a lattice spacing, which is different from the standard 1D. So this delta can be larger, or it can go down to 0 if you wish. So then you have like two atoms sitting on top of each other. And that gives, of course, an impurity, because now you have a double strength there. Oops, sorry. And here you see now this ion, this harmonic yield, this effectiveness of harmonics as a function of chain length for a certain wavelength of the laser. And you see this is what we had before, yeah, what I showed you. And now if we do this as a function of basically this variable additional kind of lattice spacing, then you see if you put them on top of each other, actually it's -1 if they sit on top of each other. It's just how you count this, sorry. Then you see you get a very high yield, and this is basically you do your tunnel ionization from the impurity, and that is much easier to tunnel because the gap is smaller. And this is the standard case. And here you get enhancement if basically you have a single chain here, a smaller chain then. I mean, at this limit, if you have a very large distance here, you essentially have two chains of equivalent length. And that gives you the standard backscattering enhancement we saw before. So this has a very interesting, of course, shape, and you can describe the effect of impurities and this backscattering in a unified, very simple setting, and try to understand this here from the simple model. So much to that. And to summarize this, so we have intense pulse coupling to atomic chain, has a characteristic length scale, n times the lattice spacing is the length roughly of the chain. And if that relates to the quiver amplitude, and therefore it adds to the momentum dynamics in reciprocal space, typically for condensed matter systems, non-trivial position dynamics in real space. We get the same strong field dynamics in terms of high harmonic generation for fixed scale lengths, and the maximal yield for the high harmonics if we have this kind of resonant conditions that the length of the chain equals the full quiver amplitude. And backscattering from chain edges leads to this extended cutoff. And that means backscattering can occur in solid state-like systems with broken translational symmetry. And this is, of course, you have the interplay here of delocalized electrons and kind of, breaks in your periodicity, which really the system or the wave packets feel then, and the quiver amplitude all of a sudden plays a big role. Okay, so this was the quiver amplitude, and next part hopefully will be shorter. It's probably already late, yeah. We come to a situation where the momentum the vector potential actually plays a big role, not just for the dynamics, but structurally. That's important now. Really, the maximal or peak vector momentum plays an important role. And this is, of course, the case. You could guess this somehow if you look at reciprocal lattices. This is momentum space. Then there are characteristic distances in the reciprocal lattice, and this should somehow also play a role. And it plays a role in graphene. I will tell you this now, hopefully in a nutshell. You probably know graphene is this kind of monolayer sheet of carbon atoms, very nicely arranged in this way. And the intriguing part is that theoretically it's composed out of two sublattices. The reason is that you cannot translate, it doesn't have translational invariance as a whole, basically lattice, so only a sublattice can be basically translated, and therefore we have two sublattices, and one is the black atoms and the other one the open atoms, and a unit cell is then composed out of one atom of each, shown here. And if you translate this now to reciprocal space, you get this typical kind of geometry here, where you have these famous Dirac points, K and K prime. And in terms of the energy bands, you do have here basically that the two bands touch each other. You have a linear dispersion, very unusual. You don't have a band gap, with zero band gap materials. And this happens at K and K prime points. And you can describe this normally in tight binding approximation. It's written here. It's not so important what the parameters are. But what is now very interesting, of course, is to calculate or think of the excitation dynamics from the conduction, from the valence to the conduction band without a gap, again, with an intense laser field. And we can very simply calculate this in this two band approximation. You can guess it's just quantum mechanics, but it's really the simplest way for atomic physics. Just solve the time-dependent Schrödinger equation. Funny enough that condensed matter physicists have much more difficulty to solve this and even to believe that this can be done so easily, because they are used to Floquet type of physics and so on. And with a finite laser pulse, you need lots of Floquet states, and that becomes quite intricate. But in principle, for us as atomic physicists, it's very easy to solve. Now, what the interesting question is here, and this is why this has attracted quite a bit of attention, is that there is a new kind of degree of freedom, which is called the valley polarization. And that is, you can have excitation essentially of initial conditions in K in this triangle. So this is the plane of initial conditions, if you wish. And in this triangle, and they are ruled by this one K point and the other one. So energy-wise, they're totally equivalent, but they have a different handiness. And therefore, it is hoped that one can store information in basically this, what's called valley polarization degree of freedom, valley polarization spin degree of freedom. And the reason why this is attractive is that this is a pure coherence phenomenon. So in order to differently populate this degree of freedom with this valley polarization, you do not need to move physically charges. You only need to change the interference of your wave packets, if you wish, your electron wave packets. And this, of course, should be fast on the one hand side and should not cost a lot of energy. But it has one severe problem. Energy-wise, energetically, both of these different values, K and K prime, they are totally degenerate, they're equivalent. So whatever you do, or most of things you do with coupling to a laser field, will essentially populate the K and the K prime excited states. And then you don't have anything to store because you cannot distinguish. So what really would like to achieve is a difference of population of K and K prime regions. And that really gives you addressable or memory kind of capable than storage. And let's see, can we actually do this? And so what we use here is now intensities 10 to the 10, 10 to the 12 to 13th. So this is pretty strong for condensed matter system, but it is believed or also measured that graphene 2D systems kind of can stand this intensity. They don't fall apart. And this is even helped, of course, by using very short pulses. So it's essentially half cycle pulses up to below a femtosecond, up to 100 femtosecond, depending on wavelengths. Normally we take longer wavelengths, which is even better to get the right dynamics. Okay, so we can jump into this. And I said we do this because there's a characteristic scale now relating to momentum properties of the laser field. And indeed, of course, the distance of these two K points, that's a distance in momentum space. And you will see this relates directly, this distance delta, to the momentum, peak momentum of your vector potential from the laser. So valley polarization, as I said, is this difference of excitation from this domain and this domain. And this is what we look now at. And if you understand this figure, you have understood it all. So I will try to spend a bit more time and then speed up on this one. So these are, again, these two triangles. Here is the K point, the K prime point, initial conditions. Now it's Q. I apologize, no longer K. I switch here between Q and K in the figure and in my description. And what we do now is we take here an initial condition in the K plane. And now we follow basically the trajectory with our Bloch acceleration theorem with A of t, how it moves. We have linear polarization of our laser in the y direction. That means parallel to K prime. And that means if we crank up now the intensity, vector potential increases and our trajectory moves here parallel in this direction. And this here you see is the crystal momentum. And essentially what happens is it passes by the K prime point. And that means there it gets excited. So the key point is that due to this degeneracy, touching of the bands, no band gap, I mean, the excitation is very efficient only at these 2 points, K prime, and it can be completely or almost completely suppressed outside if you have moderate field strengths. And this is exactly what happens here. You see, all of a sudden, if I pass the K prime point, excitation goes up. But now, of course, the laser amplitude goes down again, vector potential, so you pass it again. And here you see the excitation gets taken away again. You have destructive interference because the phase in that for this trajectory is such that you actually have destructive interference. And you can take another trajectory shown here where you have chosen that you have constructive interference. So you pass first, you get excitation burst, you pass a second time, you build up on this and get even more excitation. So this makes these ripples here. I mean, very high excitation is kind of followed by destructive interference due to the phase difference, and you get almost no excitation. And so that's the basic mechanism. You get only excitation close to the Dirac points. And since that's the case, you can even do the famous Dirac Hamiltonian, which is a linear approximation of your bands near the Dirac point. You can extend this to the time domain. And if you do this, you can actually see that you have a fully scaled Hamiltonian effective dynamics with the frequency of your laser in momentum and in time. And this is reflected here. So here we now take this dynamics to different wavelengths, keeping and also different A's. So this is our, let's call it again, resonant A. Here you will see and can guess already you have the best results for valley polarization if your vector potential really matches the difference between the K and K prime points. And you see with, almost immediately at the first glance that the pattern is kind of blurred out here for shorter wavelengths, but for longer wavelengths, it gets narrowed more and more in the X direction. And this is exactly because of the scaling here with the frequency or inverse wavelengths. And now for valley polarization, for this addressability of memory, what we would need a difference of basically warm versus black colors of excitation. And you see this is difficult here. It's almost equal, but here you can already guess it's pretty good. This is certainly more red than blue here. And indeed, that's the case. So you can see this here. So this is now valley polarization, this difference in excitation in the two triangles or the two K and K prime points, and versus the peak field strength of the laser. And you see this is for different laser pulses. Essentially, this is 800 nanometers, always half cycle pulse. And if you make the wavelengths longer, this is what we have already seen. It gets narrower, the pattern, and the difference between red and blue was larger. This is now 7.2, the green one. And the best result is this one here with the pedestal. This is done by hand. This is because to illustrate that we've understood the process. So essentially what we do here is we kind of sneak by the first Dirac point with a very low amplitude, so nothing much happens, and then crank it up later if you come to the second Dirac point. So that makes the best discrimination of excitation between the two Dirac points. And the sneaking by is achieved by a pedestal, by a basically low amplitude laser pulse in the beginning and in the end. So this gives you this one. I should mention that, as I said before, there were proposals to do this by a relatively complicated kind of clover shape circular polarized pulse. And this is shown here, the result. Gives you also some value polarization. By the way, it always peaks around this resonant condition when the field strength matches the distance between the two Dirac points, as we said. But now comes another thing you should, of course, take into consideration. We do not want to destroy our sample by actually trying to use it as a memory device. And that means the excitation should be low while the value polarization should be high. And here you see the excitation. And again, our long wavelength half cycle pulse performs quite well, while our circular pulse here from previous work is pretty bad because it always kind of excites all initial conditions. And this is something really to take into account. If you think about concepts for addressing value polarization, you should always keep in mind that you should keep excitation low. Okay, so that means value polarization requires really peak vector potential of A0 comparable to the distance between the two Dirac points. And we get the highest value polarization at lowest excitation. That means damage of your sample for pulse with the pedestal. That is for shaped pulses. One could probably optimize this just numerically by algorithms. We haven't done this yet. This is more for understanding with the pedestal. And overall, one should use moderate field strengths at a given A to limit excitation. That means one goes to longer wavelengths. Final remark here is, what is the role of dephasing? This I have not kind of swept under the rug so far. So because we have taken so short pulses that dephasing of your electron wave packet is not so important. But of course, we could go to longer pulses, and this might also be experimentally easier now since we have understood how it works. So what we need is we need an asymmetric pulse shape within a period of a pulse. And therefore, we can take multi-harmonic pulses to fulfill this. So this is simply pulse with a certain harmonic here, and we sum this up. And this gives then pulses which look overall symmetric, but within each cycle, you see this here, the vector potential is pretty asymmetric into one direction. That's what we need for this kind of transport around one Dirac point. And so this is now calculated just with the density matrix for our two kind of states and then kind of empirical dephasing term, damping with gamma 1/10 of a femtosecond. That's standard in the literature. And you see an interesting result. You see actually excitation is affected quite a bit. So dephasing is important. You get higher excitation if you have large dephasing, but the value polarization is not really affected by dephasing. That's of course good news. That means that your kind of, basically decoherence processes do not affect value polarization. Why is this? Maybe I skip this. The reason is simply that what dephasing does, it's going from here to here if you wish, it kind of blurs your excitation pattern, it kind of blurs the interferences, but this happens in the same fashion to, of course, excitation in the blue region and in the red region, and therefore the difference kind of stays the same. And that's, of course, a kind of encouraging result. And with that, I think I'm at the end. I have tortured you quite a bit. And here's the summary. So one can steer excitation in gapless 2D systems, and pulse and matter really form an integral system. You have, again, symmetry breaking through the pulse because it's a half cycle pulse effectively. And that allows you to steer now the excitation because the transition between the bands is dominantly only happening at the Dirac points. And the lesson overall is, again, that here now the vector potential of the laser pulse plays the structural role because it should match the distance in reciprocal space of the two Dirac points to be most efficient in creating this valley polarization. And dephasing does not cause a lot of problems, so you can use longer pulses. And with this, I think I'm done, hopefully. Yeah.
Thank you very much.
Oh, thanks for your attention.
Thank you very much, Prof. Rost. I think now it's a time for the questions. So those who wants to ask directly, you can unmute and then start asking the questions. Or if you want to just raise the hand or send a question on the chat, that is also fine. Professor Rost, maybe you can keep that PowerPoint online so that maybe if somebody wants to see. Yes. Yeah.
I think the graduate students must, in the audience, must have really, they must be overawed by how methods from atomic physics and condensed matter physics come together to solve very exciting problems. So fields are now merging in many ways.
Yeah, between that, I will ask some questions regarding so these kind of calculations and experiments were done on atomic systems only, not ionic systems, right?
You mean in the beginning with the clusters?
Yeah, especially the periodic atomic system, for instance, the one which
yeah, sure. So these were atoms, but I mean, with respect to how to say to the mechanisms, I don't think it would make much difference. You could, of course, have bands. You need delocalized electrons, right? And of course, this is much harder for ionic systems because it's already more charged, so it's more sticking to the ions. But essentially, you could have at certain energies excited bands then, which also are delocalized, I think, in ionic systems. But this would be excited systems where this would matter.
Yeah, especially because in the experiments, one can actually make these Coulomb crystals where we can have a certain number of atoms forming an array. And it would be very interesting to really test the theory, like very much like what would be the boundary conditions, boundary limits, how it is affecting the results and so on, isn't it?
Yeah. But then you have to think if you make a Coulomb crystal, so your lattice spacing is relatively large, right?
Yes, that's right.
Coulomb crystal. That means we would look at totally different wavelengths. This would be maybe terahertz wavelengths or so on. Yeah, who knows if this could not also be done. I have not thought about this, honestly speaking. Yeah, but there's this matching, right, of wavelengths and lattice spacing. Yeah, this was this. But yeah, who knows if, good idea. So I'll think about it.
Okay. Yeah, because especially terahertz is gaining more and more importance nowadays. So there are so many people interested in terahertz spectroscopy and the usage of terahertz for different applications.
Yeah. Think about this. That's true.
Yeah. Abhik, I think Abhik had some questions.
Yeah. Hi. Hello.
Hey. Yeah.
Yeah, you're right.
Yeah. Hi. Yeah. So I have a small question. So first of all, when you discussed about that atomic chain, right?
Yeah.
That chain, can that treatment also be extended to, let's say, like a two-dimensional system?
Yeah. So we have done this actually,
Okay.
and so the referees forced us to do this.
Okay.
And it's so we kind of anticipated the results, but I mean, one should still do it. And so because often what is wrong, right, in the expectations or the intuition. But in that case, it was actually correct. It helps even this effect, because what happens if you have a 2D system is that you have kind of an ion channel almost. That means your wave packet, if you think of the electron wave packet being driven back and forth, right?
Yeah.
Your polarization. Of course, you have spreading of your wave packet laterally. And that is kind of a very negative effect on the intensity of high harmonic generation already in atoms. So on the way back, to the ion, your basically continuum electron wave packet spreads, and there's much less density, electron density, continuum density recombining with your ground state wave function than you would like to have, because most of it is spread out and not overlapping with your bound state wave function. Similar thing is happen, of course, here. But now it's the positive effect, because your lateral extension, your ions, they give a binding potential. So that kind of limits the spreading of your wave packet going into the X direction, limits the spreading in Y. And that means you get actually a higher yield of your extended plateau harmonics. Okay. And the thing happens again. 3D, honestly, we could not do, because we didn't know how to solve this with finite thing and getting to the periodic limit. But 2D is fine, and I think there's not much difference than to 3D, because this effect of guiding your wave packet in the direction where it does not propagate is probably the same if you add another one. Yeah.
Okay. Thank you.
Yeah. Any further questions? Okay. Yeah, I think I don't see anyone else. Okay. Yeah, I think Professor Deshmukh, we can then conclude the section.
Yes, I would think so. It's
okay. Yeah. Professor Rost, it was a fascinating talk, and thank you very much for your time on this Saturday when you are really not working. So it's unfortunately probably for Indians we have to work on Saturdays too. Yeah.
Don't worry, I also work on Saturdays, so I'm used to do this. My advisor used to do this, and so I kept this most of the time. Okay, with family it's sometimes a bit different, but still, no, it's no problem. Yeah, so thanks so much for listening and for the invitation again. So I have one last question. How warm is it at your place? What's the temperature?
Okay, now it is 30 plus 30-35 in between.
30-35.
It's not too bad now, actually. It's not a hot time.
Very good.
Yeah. And there are some occasional rains, so it is keeping it cool.
Okay.
Yeah.
You could send up.
For us, it is actually a good, even if it is 30, we are lucky.
Right.
So, not like in Germany.
Very good. Yeah, you could send us some of your heat. This would resolve our problems with the gas.
Right.
Okay. Yeah. So thanks a lot.
Well, I should mention for some of the graduate students who may not be knowing, Professor Rost is also one of our advisors for the Center for Atomic Molecular Optical Sciences and Technology. So it's very kind of you and very generous of you to be available to guide our young students.
Yeah, my pleasure.
Yeah, so
thank you very much. We have been waiting for this talk for some time and really enjoyed it very much. Thank you.
Okay, thank you. Bye-bye. Take care.
Bye-bye.
Okay, I think now we can stop.
Yeah.